a friend of ours, Valeria Pettorino, and she got her PhD in Federico University. Her list of the things on the CV is too long for me to go through all of it, but she has a lot of achievements, Marie Curie fellowships, CISA Young Scientist. She has been involved in both Planck satellite and Euclid. Um, she also does a lot of outreach activities for the community. She did the Euclid. She has been a Euclid deputy for public outreach. And I guess maybe I get to the actual work that we are doing together, which I feel like has a very important, and maybe she will say a few words about it. Valeria and I have been working together in this mentorship program for women in physics together, which now we have, I don't know, 300 or more mentees. And more importantly, I think one thing which is of interest of people in Waterloo, she visited us a few years back, and she certified our pizza place Famoso as a good Napoleon pizza. So you're allowed to go and have pizza there. And with that, I leave it to Valeria.
Thanks. That I couldn't remember that, but that's really a thing that fits what I would do. Go to a pizza place there. So thank you very much, everyone. Thanks, Ghazal, for the nice introduction and for the very kind invitation. It's always a pleasure to be even virtually in Waterloo. And also a nice memory, because you might not know, but during high school, I was actually living for a while in Cambridge, near Waterloo, and I visited Waterloo University at that time when I had to choose what to study afterwards. So I remember very well that day in which, again, I went to Waterloo University. And that was long before also, I don't know, Perimeter Institute ever existed, I think. So I will talk today about dark energy from theory to data. I'm Valeria Pettorino, and I currently work at WCA in Paris-Saclay. Do you see the slides moving?
Yes.
Okay. So I'll introduce quickly myself and the Cosmostat group in which I'm working currently, and then I'll tell you something about theory, something about statistics, and something about observations, because across the years I ended up working a bit at the interface across these three different aspects, which somehow are sometimes attached to different communities, but at the end work together to address the same quest and the same challenges. So that's a bit an introduction about me. I'm a physicist and cosmologist. As Casal said, I got my PhD in physics in Napoli, in Italy in 2005. And then I moved around in different places, in Switzerland, in Geneva, in Germany, in US, and I am in France since now 4 years at WCA, at the Department of Astrophysics. I started working on theory, on theoretical dark energy, on modified gravity theories, on the theory of the CMB, on neutrinos, on cosmology, and also in astroparticle physics, especially at the beginning. And then I got more and more interested in data. I was part of the Icarus collaboration, and then of Planck and Euclid. So for Planck, I led the dark energy analysis, and for Euclid, I got involved in several aspects, from theory to forecasts to the likelihood to cross-correlation with CMB. And right now I am co-leading the Interscience task force. I see there's also people involved in that task force now here in the audience, which are very active. So I think sometimes somehow across the years, I worked more and more at the interface across theory and data. And I also tried always to engage a bit in things which were a bit beyond or across disciplines. I was, for example, board member for a while of the Euro-Python Society that tries to encourage the use of Python programming language in different contexts and applications, also outside academia. And I worked on a healthcare project for a startup in a data science program. I've organized for several years a school on cosmology, which follows the motto theory for observers and observations for theorists. And then I also got engaged in generally networks that somehow have host people across different domains, from NGOs to UN, ESA, or different professions. And one of these networks, and about which I'm really happy to be in, is the mentorship program that Ghazal was saying, the Supernova Foundation. And I really learned also a lot from Ghazal, who is really active and a lead in this program. More recently, I also got engaged in science policy and in science diplomacy. And actually, if there's anyone who is speaking Italian, there's an event that I'm organizing next week on science diplomacy and space exploration, which is open to everyone who might be interested. And that's perhaps then not by chance that I ended up in working as the staff at Cosmostat and at WCA, which joins a bit statistics, cosmology, academia, and also applications outside cosmology in neuroscience or even in industry. There's about 20-25 people now in Cosmostat, which are working on different aspects in cosmology, on signal processing. There's 39 software packages last time I checked, which were made publicly available. And we also arranged for different tutorial sessions for scientists, which were made available, especially during lockdown, on the Cosmostat YouTube channel. So across this talk, I will reference works and results that have been done, of course, with different collaborators, partly on theory, on statistics and machine learning, on Planck, on Euclid, and simulations that were used in order to actually produce these results. So let me mention in particular Virginia Ayani. I will say more about her afterwards. She's my currently PhD. And also Santiago Casas, who's currently postdoc with me. So let's move now to cosmology and to the standard cosmological model you're certainly familiar with, in which we know that the universe is currently going through a phase of accelerated expansion, although we don't know what actually causes cosmic acceleration. We know that the universe is spatially flat, but we don't know what's in it, and whether there's more and what it is beyond ordinary matter. If there's dark matter, what is dark energy? Is it a cosmological constant, so a constant contribution in time and space that you add in the equations of general relativity, or something more? So of course, a cosmological constant, it's in practice a parameter that fits the data. And that was not trivial to achieve, in the sense that it was not meant to fit all this data. And it's still, I think, not only surprising, but I mean, really impressive, the fact that after so many years and different data sets, it still is a good fit to the data that are available. At the same time, it doesn't really match any satisfying theoretical prediction. It requires great fine-tuning. It marks the present epoch as a very special time in the universe evolution. And also somehow the whole pipeline that goes from data to theory has been mainly tested for lambda CDM, let's say. So it's which is already quite challenging. So that all these reasons have motivated the community to go beyond cosmological constant and wonder whether there can be a dynamical, say, changes in time and space associated to what causes the cosmic acceleration. It could be interpreted as a fluid, so as dark energy, or as a force that adds to the ones that we know. And at the end, what we want to test is really interactions, forces at cosmological scales, as we would do in particle physics, and also value the complementarity of the different probes in terms of scales, in terms of epochs that we're testing, in terms of the physics, of the physical effects that we are actually observing, because they carry, again, different information. There's at least two different questions that we can ask. Can we falsify a cosmological constant? And can we distinguish among the alternatives? And although, I mean, I would be happy to know the answer to either of them, and I don't, but the point I want to make is that they may require different strategies depending on the question that you actually want to address. And usually this is attached to three tails that go in parallel for the same quest. So one side, there is, as a theorist, you can try to figure out new ideas and new theoretical models, which need to be convincing first for the theory community, and then that can be tested and that can at least match all the data that we have so far. The other side, there is the methodology, the data analysis, which comes in between, in a way, the development of numerical codes, their validations, the statistics that imply different choices that have to be made during the process of the data analysis, and that can have an impact on the final results that you have. And then third, there is the experiments. You can look for more data. You can try to get a higher frequency coverage, or to look for a full sky survey as opposed to ground-based observations. And all this somehow goes in parallel, because on one side, as a theorist, you want to be aware of what are the assumptions which are made in the experiments. You don't want to misinterpret I don't know, systematics for new physics. On the other side, as an observer, you don't want to go into fishing expeditions or end up with things that have perhaps already been excluded, even at the theoretical level, or that nobody cares about. So in between, again, you want to be aware and make really transparent what are the choices which are made along the way, and trust the numerical say development, which is in between the two, that links the data to the theory. So I'll start with the first of these three tails and highlight some of the recent contributions that I gave on these three different aspects. So on one side, I start with the theoretical cosmology. And in theoretical cosmology, there's two ways in which I've been giving my contribution in theoretical cosmology. Sometimes starting from an action, so starting from a specific cosmological model in which you derive all the equations for the background, for the perturbations. You try to modify, for example, Boltzmann codes, and then you try to predict what are the theoretical expectations specific for that model in the linear regime and in the nonlinear regime. And I did that for different models. Among them, I will mention in particular coupled dark energy. But I mean, in general, there's, in particular for Planck, I've been working on many other aspects, and also again, general Ordinsky theories. On the other side, so in this case, we're rather trying to answer the question of which is the model that actually fits the data, that actually works. But on the other side, sometimes I've also worked more on the phenomenological, at the phenomenological level. So in trying to find generic functions of the perturbations of the gravitational potentials, typically different functions of the matter power spectrum or of the lensing potential, that can be used as a way to disprove lambda CDM. So functions that perhaps are, say, equal to a certain value, to 1 in lambda CDM, and that instead would be different from 1, from that value in alternative models. It might be more difficult to identify which is the model that actually fits, that actually works, that is the true one, but at the same time, it answers to different questions. It's perhaps a more adapted strategy if you want to first answer to whether you can disprove lambda CDM. So I'll, however, discuss one example on the left side. So starting from an action, because recently, together with postdoc Adria Gomez in Heidelberg, we updated the constraints on coupled dark energy from different data sets. So coupled dark energy is a model on which I've been working for many years. It's a model in which you start from a Lagrangian in which dark matter mass changes with time. It's a function of a scalar field that behaves as a dark energy fluid and provides cosmic acceleration. It is associated to a fifth force that adds to gravity. And after, again, the updated constraints that you can find in these recent papers, it is still compatible with all the current data that we have so far. It was in particular interesting to look at and update these constraints in view of the fact that there is a degeneracy between the coupling, so the strength of this fifth force, and the expansion of the Hubble parameter. That was actually something that I pointed out in 2013, so long before there was even an interest, attention in H0, but as you know, right now, it's instead became a thing, the fact that there is a tension between, which is now at almost 5 sigma, between the values of H0 that are found in Planck, for example, from CMB experiments, and the one that, for example, is found by Shoes from direct measurements from supernovae. So there is, I don't want to discuss about that. There's different reviews of data and theories to which I actually also contributed. But what I wanted to point out is rather that in coupled dark energy, the coupling modifies your matter power spectrum and enhances, depending on the strength of the coupling, the growth of perturbation in a way which is similar to the effect that neutrino masses would have on the matter power spectrum, in particular in the nonlinear regime. And this is why, if you know the physical effect that produces this degeneracy, then it's not so difficult to find 3 models, one of which is lambda CDM, and 2 of which are coupled dark energy, which are still compatible both with the CMB and for the same values of the parameters, also with the matter power spectrum. That's again because there is a degeneracy between the strength of the fifth force and neutrino masses. So I can still be within values which are accepted by data for neutrino masses, but still find, have larger fifth forces if I also have larger values of the neutrino mass. I'll come back to how we can actually, hope to break this degeneracy. But for now, I wanted to mention that what you'll find also in this recent paper is how this compares with different data sets. In principle, you find a peak corresponding to a value of the coupling beta also larger than 0, which is more or less evident depending on the data sets that you include. If you include usually CMB lensing, that's the one that squeezes everything towards lambda CDM. But when you actually do compare the models with the model selection criterion, which is based on the full patient evidence, as you should do, then lambda CDM is still anyway preferred in all cases. So does that mean that it doesn't help? I must say, in this form, no, I don't think it helps. It might help if one had, for example, again, a coupling which is not constant, but which might change in time. Still, it's something that again, it's a framework that is still compatible with current observations. And yet, I mean, the statistics which has been applied, of course, also makes a difference also with respect to other works on the on this topic on your result. One interesting aspect was also that the coupled dark energy is what I would call a forced accelerated model. This is something that goes back to a concept that you might have, you probably have heard of, which was a few years ago, quite popular, of self-acceleration. That was originally introduced to distinguish what is genuinely let's say, to distinguish what causes cosmic acceleration, whether it's a genuine modification of gravity or a cosmological constant. And although it's fair enough to ask these questions, the original definition that was used was a bit problematic in the sense that, as we showed in this paper with Luca Mendola 2 years ago, first, it was only applying to universal couplings, and second, it was too narrow in the sense that it was leading to discard models even when it could be actually proved the acceleration could be actually shown as a genuine modification of gravity. And so that's why at that time we introduced these new concepts that somehow address the same original motivation, but can be applied for like any theory that you might have also beyond the universal coupling. So there is a practical, let's say, recipe to decide whether it's forced accelerated or fluid accelerated. Now, usually when I discuss about theories, depending on the audience, or theories beyond the lambda CDM, especially if I discuss that, with people in my group, which are also more expert on observations or on statistics. One of the fear is that models are, too exotic. Now, although as a theorist, there's lots of worries about different models that I will discuss in a moment. Being exotic for me has never been somehow an issue. And the reason is that if we were on the 96% dark side, if we were made of dark matter or of dark energy, and we would look at 4%, then we would find lots of, again, 4 fundamental forces, lots of particles, and the whole standard model of elementary particles that took quite a while to actually discover. So in a way, we are much more exotic than any dark energy or modified gravity model that has ever been proposed, probably so far. So being exotic, for me, somehow it's not an issue. I'm rather worried from a theoretical perspective on other things, on the fact that the equations are usually very complex, that when you start from an action and you have to derive all the perturbation that, can be very non-trivial, that they're difficult to test because first, also for practical reasons, because often they're left, it's like modifying Boltzmann codes to include all these equations is left to theorists, and I don't know, but I'm not a software engineer, so I'm very inefficient in this process, and I have to validate my codes to actually be able to trust them. There's very few n-body simulations beyond the lambda CDM. It's hard to predict the nonlinear regime and the theoretical predictions in that regime, even if you had all the systematics under control. I have sometimes a hard time in trusting even the theoretical prediction at nonlinear scales. And also, usually they involve extra parameters up to several free functions, and including that in a Monte Carlo can take days or even weeks. So there's, which again makes it even harder to test models beyond lambda CDM. And finally, there's lots of assumptions that also worry me in this, and in this as a theorist, in the sense that I want to know exactly what was assumed in a data analysis. And the more I got to work with data, the more I realized that there are choices that are made. And I want to know which are the theoretical assumptions which are made within the data analysis to know if, for example, when I'm inserting CMB lensing, this is already assuming some, again, lambda CDM or models which are very close to lambda CDM in building the likelihood. So that brings me to a bit the second of these tales, which is the methodology, the statistics, and the choices which, again, are made also within the data analysis. And this can, this led actually to several papers together with...
Sorry, Valeria, do you mind if I interrupt you, ask a question about the previous part?
Yes, you wish, sure.
So I was just wondering, so is the conclusion then is that there is evidence for coupling between dark matter and dark energy, but it doesn't address double tension? Is that the conclusion?
So I think I wouldn't say that there is evidence. I think that it's still compatible and that more data can constrain it further. And I think there's, at the moment, I don't think there's, this is an evidence in the sense that if I compare the different models and I use a full Bayesian evidence, then models which have obviously like more parameters like coupled dark energy are automatically weighted less somehow. They're penalized for that.
Right.
And so at the end, lambda CDM is still preferred based on this analysis in all cases.
Okay.
Model selection, of course, has an impact in other papers where they claim that also coupled dark energy could have been a solution. For example, they were not using, well, first other assumptions and then also other methods to select the model.
Okay. Thank you.
Welcome. There's another question. I see your hand raised.
Oh yeah, I was just going to ask, is there, I mean, these are comparisons or constraints from the CMB or large scale structure. What's the smallest scale on which there's sort of different phenomenology for coupled dark energy and dark matter?
So this, in here, we included also, well, different combinations and also different, so not only CMB, but also at different steps separately, galaxy clustering, redshift space distortions, and also separately the effect of adding Schulz and Holy Cow. For the scales, and we, let's say, try to be conservative, but in this specific case, we have embodied simulations as well that we could use. But I don't remember exactly up to which nonlinear scale we got, but I mean,
is there any physical difference below, say, 10 megaparsecs or 100 megaparsecs?
On the theoretical prediction, yes. So you can change, for example, you can change the position of and the amplitude of the BAO fixed oscillations in the spectrum, and then afterwards it depends if you trust it or not. But I mean, it depends. So at very let's say at smaller scales, or when there is clustering, you can change the concentration of the halos. For example, you can change the number of clusters that you would expect. We had some also analysis on that based on embodied simulations. So you would modify also, for example, the number of clusters, the number of halos that you would expect at different scales. Okay, thanks. That's in the simplest framework in which the coupling is a constant at all times, and it doesn't depend on the scale. And there's more complicated and perhaps more motivated frameworks, like in the growing neutrino scenario, for example, where instead this this is expected to actually change in time, like starting from a particle physics model. But originally, this was, let's say, the simplest one also to implement and for which embodied simulations were available.
Yeah, can I also ask a question on that?
Yeah.
So it was beta 0 lambda CDM limit, or?
Yeah, beta 0 would correspond to lambda CDM. There is an extra parameter, however, that is in the potential, in which a scalar field also rolls, but usually this has a very little impact. So in this specific plot, beta 0 would be lambda CDM.
So am I reading it right, that if I allow for beta to vary, the beta non-zero beta is preferred to 0? Okay. To 0?
Well, here it's a constant, so it's assumed to be constant. So it might change if I have different, if beta is changing with time. In fact, what I would do personally is to test at different epochs how big the coupling can be.
But if it's not time dependent, a non-zero constant is preferred to 0 constant. Is that correct interpretation?
I can't. I don't think I can say that because this assumes already that beta is constant. If it's not constant, then I mean it might depend on which epoch and which data sets I'm using.
If I keep it
I
constant,
think just Azal is saying that there is a peak that's not 0 at some non-zero
Yeah,
value.
this is when I include also shoes in particular and holy cow. And in general, yes, there is a peak, but again, I don't think it's significant enough to say that it's preferred with respect to lambda CDM, because even visually it might look like at the end, if you apply the correct, I mean, if you apply full Bayesian evidence, then that's not the case.
okay, I see.
Okay, so I'll go to the second part, which is on the methodology and statistics and on works that I've been doing mainly in the recent years. When I arrived at Cosmostat, where they are very expert on, again, different statistical methods for different applications, and also, I mean, while working for Planck, I realized that, of course, there's different ways in which one can analyze the data. So which one should I use and how much does that impact the final results? And statistics in general and the choices that you make can help with missing data. For example, if you're reconstructing the shape of a galaxy, of course, you don't observe directly the shape of the galaxy. You have to reconstruct it. And if you want to separate the signal from foreground components, like you would do, for example, in CMB, like we were doing in Planck, then of course statistics and different methods can help with that. But also, as I will show in an example in a moment, statistics can help to discriminate models, to break those degeneracies that I mentioned before. And of course, it opens new challenges, the numerical challenge, the expertise which is required in understanding and implementing all the different statistical approaches. So most of the results that I'll discuss here are made thanks to my PhD student, Virginia Ayani. She's ending at the end of the year and she's currently also applying for postdocs, and I highly recommend her because she's great. She could do everything. I think she started with dark matter theory and then became expert on weak lensing and different statistics. And she's also one of the most active members in the Euclid likelihood team as expert for weak lensing. So specifically, for example, for weak lensing, and I refer to here to cosmic shear, so to the distortion of shapes of distant galaxies that we observe, distortions which is due to large-scale structures along the line of sight. So when we look at this, at weak lensing, what Virginia did is to build a pipeline that goes from the convergence maps, and so that can be taken from simulations, or also recently she is starting to apply that to data, to the CFIS data. Like she can extract different summary statistics for weak lensing, apply a likelihood, and extract uncertainty on cosmological parameters for each of these statistics. So one example of application of this is in this paper, in which we focused on neutrino masses for the moment in lambda CDM. So in this case, she could use the pipeline to forecast how different statistics would perform in constraining different cosmological parameters. So she took noiseless, initial noiseless convergence maps, applied noise that mimics what Euclid would do to get noisy convergence maps, starting this from simulations that were provided by the Columbia Lensing group, which are great because they vary 3 different parameters and contain 101 different cosmological models, which is actually pretty rare. And we could profit of that. You can then filter your convergence maps, and there's different ways in which you can do that. Also, I mean, she compared, but in practice, you then have access to different scales, and you reconstruct your aperture mass maps after filtering on your convergence maps. When you do that, then you can apply different summary statistics. You can start from second order, then third, fourth, or you can count peaks. So you can describe look at the distribution of local maxima. So she did that for different statistics, applied the pipeline, calculated the likelihood, and extracted uncertainties. So forecast, in this case, for, again, a noise level of, for example, for Euclid on cosmological parameters. And this allows to then compare different say, constraints, depending on the choice of statistics that you have used, starting from the power spectrum to single Gaussians, multi-Gaussians, or changing the filter from Gaussian to starlet. So in an ideal setting, then peak counts, for example, was performing, let's say, better, and I mean, potentially could extract more information from the nonlinear scales. In addition, depending on what you use, and even, for example, on the filter that you use, you might get, for example, a faster covariance, in the sense that although there was not much difference in the final cosmological constraints, Virginia noticed, for example, that most of the cosmological information in the data covariance matrix was actually encoded in the starlet filter in diagonal elements. And this basically has an advantage when you have to invert the matrix and speeds up the numerical implementation. So on one side, she could compare different statistics and show how your constraints can change depending on what you use. And on the other side, also identify which are the ones that might be more, let's say, convenient to use also numerically. Recently, last month, actually, in ANA letter, we also proposed a new summary statistics for weak lensing, which is based on a starlet L1 norm that in practice avoids the problem of even defining what is a peak and what is a void, and so fixing a threshold, because in practice it includes all the pixels in the map. And this on one side can lead to even tighter constraints than peaks, but on the other side loses a bit this feature of information being encoded mainly in the diagonal elements. But in general, higher order statistics, provided that all the systematics are under control, are a promising way to access the nonlinear cosmological information. And in any case, it's a choice that you make within the analysis, and depending on, again, what you actually want to test and which scales, it can be more appropriate to use one or the others. But also, statistics can help in actually breaking the degeneracies between different models. And I want to show you how I propose to apply that to break the degeneracy that I was mentioning before. So the fact that when you have a fifth force, this is usually degenerate with massive neutrinos, because they both tilt the matter power spectrum. And for example, so to investigate that, together with Marco Baldi, we designed a set of simulations that were meant to be degenerate with lambda CDM. So one side lambda CDM, on the other side, in this case, FOVAR models. So what you probably all know, but I mean, in which there is a universal coupling with a fifth force for different values of the neutrino masses. And we were expecting, in particular, we saw that this, at the level at least of the matter power spectrum, a value of FOVAR with the neutrino masses of 0.15 electron volt would be difficult to distinguish from a lambda CDM. So we did that in order to investigate what was the main degeneracies and how we could devise strategies to actually break them. We then profited somehow the same kind of pipeline and investigated different statistics. And when you look at the variance, so I mean, second order and matter power spectrum, as expected, you see that your lambda CDM, the gray distribution, overlaps with the green one, which is the one for 0.15 electron volt in neutrino masses. The others are a bit less degenerate as you decrease the value of the neutrino mass as expected. If we apply a different statistics, I mean, we tested different ones, but in particular, we noticed that if you instead choose peak counts, so count your peaks in the mass maps, then lambda CDM can be very easily distinguished from any other FOVAR models, including the green one that was degenerate at second order. So in this case, peak counts are better at distinguishing lambda CDM from FOVAR, although it won't help in distinguishing different FOVAR models. And you might notice that, I mean, this is at the end a classification problem for which the next step was to see whether machine learning could actually help even more. And in this case, you see, we then applied the convolutional neural network meant to, again, resolve the classification problem. And this is a confusion matrix. So you see on the rows indicates what's the true model, and the columns correspond to your prediction. So in principle, you would like this method to be efficient in assigning your prediction to the truth. And the more efficient it is, the more the confusion matrix will look similar or close to an identity matrix. Because again, you want the prediction to be assigned to the correct model. And you see, even just, I mean, by eye, that with respect to big statistics, this is closer. In the case of a convolutional neural network, the confusion matrix is closer to the identity matrix. Also, for that model, the one with 0.15 electron volt, that was more degenerate at the second order with lambda CDM. So here you have 90% of probability to get the right to distinguish them correctly. This is for a zero, like ideal zero noise level. We also tested different levels of noise. And of course, this efficiency is degrading the more noise you add, but still the CNN is behaving better than peak count and still better than random peak. If you really add a lot of noise, then that was 70% of a signal given by noise, then peak counts are basically only a random peak, and CNN is still a little bit better than that. Finally, there is, I like to mention perhaps something about the last part, the last stage or the experiment, because that's by itself a huge challenge. It's a huge challenge in the technology, in the systematics, and also in the choice of the observables that can actually help to test your different physics. And in particular, I've been very much involved in the Euclid, for the Euclid satellite, which I think you know is ESA, NASA medium space class space mission, selected in the program Cosmic Vision, and the plan to be launched in space at the end of 2022. primary probes would be weak lensing and galaxy clustering, so to measure the expansion and the growth of structure. Here are a few pictures of the Euclid NISP, the Euclid Near Infrared Spectrophotometer, which was done in Toulouse and delivered to ESA in May 2020. That's how it looks inside. It's actually like, real now. And the Euclid VIS, the visible instrument, that was also delivered to ESA in July 2020. Both are then mounted on the Euclid payload module. There was an ESA press release about that also in July 2020. And yeah, that's how the Euclid payload module is meant to look like. Wait. Okay, what I want to mention is that in particular, something that can be useful beyond Euclid, which is the forecast validation that we did for Euclid cosmological probes. So it was a huge effort to validate, let's say, forecasts. So what Euclid could do when to test actually cosmology using different probes, galaxy clustering, weak lensing, and their cross correlation. And when we started, it didn't seem so difficult, honestly, but the problem was that there were many different results, even different papers, published papers, which were claiming different things, and in which, at the beginning, when we investigated forecasts, lines that should have overlapped did not, in the sense that they were all, let's say, different in amplitude and even in the degeneracy direction. And this led to the science working groups to join their forces into the Interscience Task Force to actually see how we could validate forecasts, arrived forecasts and predictions that we could actually trust. That required a lot of work to define the recipe, so the actual equations that you need to take into account for galaxy clustering, for weak lensing, and for their cross correlations, including systematics. Also, the strategy to address, to include nonlinear corrections, which requires two different recipes, depending how far you want to go into nonlinear scales, whether you are interested in galaxy clustering or weak lensing, and defining an optimistic or pessimistic scenario. We compared the different codes which implemented the same that recipe, and up to when they were actually validated, in the sense that they were they had a difference of less than 10% on errors on each parameter. And the main point, which I think at the end is also the main output, is that this is available now also for other collaborations, because it's, and in particular in the appendix, that perhaps not everyone notices, but I think it's actually the main delivery of this paper, which explains how you can do your own code comparison, how you can produce and validate and trust your own forecast, not necessarily for Euclid, but also for other collaborations. And includes also the reference features and also how to produce, for example, a plot like that and add your own code into this plot, comparing it with what we had for each parameters in each plot. So this shows the percentage differences on the errors for each of the parameters and for different codes.
Is it, sorry, Valeria, is it like very like data specific, like certain kind of data sets, or?
So this in here we included galaxy clustering, weak lensing, and also their cross correlation. And then there's a follow-up paper that also included cross correlation with the CMB.
Okay, that's the one you included is cross correlation between galaxy
clustering and photometric spectroscopic galaxy clustering and weak lensing.
Okay.
And this is at the end. So after this work, I basically, right now, I have first the difficulty in trusting any forecast, which has gone through some kind of validation, because it was absolutely incredible how long it took to actually, I mean, and how many problems there were in actually modeling this. And second, I trust this plot where, again, there is also the impact of the cross-correlation in the photometric part. That shows also how important it is to include cross-correlation, in particular if you want to test models beyond lambda CDM, because already in W0 WA, we had an improvement of a factor of 3 in the figure of merit when you include cross-correlation with respect to just adding them up, although again they're not independent. Okay, so that's now, I mean, available also to the community. So in conclusion, I think you can start from what usually people start from, a scientific idea, and then perhaps they propose an experiment or a test for that idea, for that scientific hypothesis. And then there's, of course, the challenges related to the technological development to actually realize that idea and that experiment, to collect the data. But there's also the whole signal processing part, the choices which are made in data analysis, in reconstructing, like going from the data to something that you can actually test and compare with the theories, in the statistics and in the systematics that are involved. And all of this then can lead you finally to interpret the data, to compare it with different theories, to revise perhaps or propose a new experiment, and if you're lucky enough to find the new fundamental physics. But all these parts, I hope, I mean, I made the point that they all contribute to this quest. They all imply different choices that you can make, and I think it's good to be aware of what the others are doing independently on which part of this chain you're working in. Because this can actually have an impact on the final results. Okay, so I think I'll stop here.
Okay, thank you, Valeria. Give you the manual clapping. Feel free to give virtual or with sound clapping to Valeria. That was very nice talk, overview of all the way from theory to data. Do we have questions? Feel free to either unmute or raise your hand. Maybe I ask one question and then we wait if have other. So how much computationally expensive is it if you want to go down this higher order statistics methods? Like, are we hitting the limitations, or still a long way to go?
I think right now, again, in an ideal setting, it's not really numerically challenging in the sense that the pipeline is in place. The problem is more with the problem is more, I think, with the theoretical predictions at nonlinear scales, and with adding also the effect of systematics, like intrinsic alignment, for example, that also has an impact. But otherwise, it's pretty fast. Well, especially the machine learning exercise to distinguish different models, it's very fast.
So is it like writing the right likelihood from the theoretical aspects, and then do I understand this correctly, or that's the part that is more challenging? Like when you don't want to do the nonlinear scale? I
think, yeah, nonlinear scales are challenging both for the theory to actually, I mean, have a prediction that corresponds to the model you have, to implement, because sometimes you have to rely on n-body simulations, depending on how far you want to go into nonlinear scales, and for the systematics, because, for example, intrinsic alignment or baryonic effects can have more impact at smaller scales. So somehow that's the regime where there's more information but at the same time, it's also the most challenging part. And right now, the problem is that often we discard data in that part because we don't know how to actually use them, or actually how to actually interpret them. And of course, I mean, that's an issue, that's a problem, because I mean, we gather more and more data, but then if the point is rather in the statistics or in the theoretical predictions, then it's also a pity not to actually profit of all the data that we gathered. So it's not just about getting more data. I think it's also about solving all the other issues on the systematics, on the theoretical predictions, and on linear scales.
Andre?
Hi. Yeah, I have a question about these validated forecasts, and maybe just out of curiosity, how do they compare with like the white paper forecasts with Euclid, let's say? Were there any like surprises where like, were the original white paper forecasts accurate, let's say? After this code comparison, it's a bit.
So let's say that at the end, it can still manage to have the same figure of merit, and in fact, it can even be improved with respect to what had been forecasted originally in the Red Book, if you include cross correlation. And that was the first time that we had done that we shown that. When we started, we weren't sure whether cross correlation would have actually had such an impact, and that's also why we tested it on W0 WA, because that had been tested before in, like, those are parameters which have been tested before in the Red Book. So okay. I think it helped to even improve the results that were originally forecasted.
Okay, great, thanks.
Okay, any other questions?
Yeah, hello. So I have a question.
Yeah.
Okay, so just I remember like reading the Euclid forecast paper. So I was just wondering, so I mean, because I remember like the forecast constraints are actually really, really tight, even in the pessimistic case. But so I was just wondering, like, so do we really trust the results? Because I think I remember, like, if you just compare like even the pessimistic case with, current Planck, it's already better than current Planck, I think. I mean, if memory is correct. So I was just wondering, like, so are we really certain, like, for example, when we actually get Euclid data, like, at least the pessimistic forecast will happen? Or is this still like, just like, are we sure like we are going to get such amazing results? Basically, that's my question. So
I trust the way in which they're done now. I trust them. Before, again, before not, but right now I trust the actual pipeline and the different codes that went through this pipeline. Then of course it depends on the actual specifications, right? I mean, in the forecast you have to pick a number density that you actually observe, or you have of the redshift that you're actually going to observe. So hopefully this will correspond to what Euclid will actually measure in terms of, again, number density. So if the specifications are still valid, then I trust the forecast that come with it.
Okay, so also the second question. So I noticed, like, in the paper, I think I remember, like, actually, so like for the reionization optical depth, like the parameter is fixed. So I was wondering, like, so what if like you choose a prior, for like if you choose, for example, current Planck prior for the optical depth parameter, like how much of like the forecast will actually change for all the parameters?
Well, the Planck prior would, of course, somehow with tight. There's a second paper, which is not this one, but in which there was also cross correlation with the CMB, and it would help in constraining omega baryons and in breaking some other than degeneracies with other parameters. But yeah, I think, yeah, partially you might. I mean, I think you could still gain a bit depending on which parameter you're interested in.
Okay, thank you.
For example, also, yeah, massive neutrinos. In that case, it would help. If you include, for example, CMB lensing, then that would also help for if you're interested specifically in massive neutrinos.
Yes, thanks.
Any other questions? Not, let's thank Valeria one more time.